Chintan bhai.
Good afternoon, everybody, and pranam to the dignitaries present online, members of the IAPT office bearers, and faculties and research scholars joined online on YouTube. Today, we celebrate a Pi Day, which also coincides with the birth anniversary of the genius Albert Einstein. Good afternoon, everybody. Am I audible, sir?
Yes. Continue. Please continue.
Okay. Yeah. Yes, sir. So today we have with us who knows Einstein more than anybody else, Einstein and his word. So I may say, and who has also authored more than 20 books and 170 research articles. We have with us Professor Ajoy Ghatak, who needs no introduction. So first of all, I would like to invite Professor K. Josipura, sir, to address the gathering and then call the speaker. Welcome, Professor Ken Josipura, sir. Sir was a immediate past General Secretary of IAPT and a former professor at Sardar Patel University, Vallabh Vidyanagar. Welcome, Josipura, sir.
Thank you so much, Chintan, and all the friends over here and on the YouTube. I'm so happy to welcome one and all. And it's a special pleasure to welcome our guest speaker of today, our noted physicist and a well-known speaker, Professor Ajoy Ghatak, who is going to tell us about the Year of Miracles, Albert Einstein's Year of Miracles. I'm not sure whether our RC president, Professor Vinod Kumar, is here or he might be joining. I'm happy to welcome Dr. Praful Desai, our secretary, Dr. Chetan Limbachia and others. And it's a pleasure to be here with all of you. Albert Einstein, birthday, March 14. This day in 1879, Albert Einstein was born, and that was the year in which James Clerk Maxwell passed away, leaving the legacy of the speed of light. And then the legacy was further taken up by none other than Albert Einstein. In fact, I read that as a teenager, Albert Einstein had a wonderful sense of imagination, and he imagined what would happen, what would I see if I were to chase a beam of light with the speed of light. See, that was a wonderful imagination. This is what I've read. And in the later years, Einstein had said that imagination is more. He has demonstrated this. The turning point for the world and for Albert Einstein himself came in 1905. And so we have Einstein's Year of Miracles, miraculous years. Epoch-making discoveries were made, and our speaker is going to tell us about this. That was 1905. The centenary of that year, that is 2005, I recall, was celebrated in our IAPT Regional Council, Gujarat Council, with various programs. And the first ever program in that series of programs in 2005 was a lecture by Professor P.C. Vaidya, who was our legacy to Albert Einstein, because P.C. Vaidya had worked on general theory of relativity. And in those years, 2005, several programs, competitions for the students were organized throughout Gujarat. That was 2005. Even in 1905, the world changed. In the 100 years after that, the world changed. And the world has changed dramatically after 2005. I don't think in 2005 or so, we had imagined having a two-dimensional meeting like this, but now it is possible. Now it is here that not only light, not only picture, but sound also travels with the speed of light. See, that is great. That's indeed great. So with these few remarks, it is our great pleasure to welcome Professor Ajoy Ghatak, There is always a joy of learning, when Professor Ajoy Ghatak is speaking. And we have one more occasion. So thank you very much. I would request Chintan to please proceed further. Welcome one and all. Thank you so much.
Thank you.
Thank you, sir. Now I would like to move ahead and I would like to request Dr. Pruthul Desai, sir, to introduce formally our speaker. I know Professor Ghatak, sir, needs no introduction, but still to formally introduce the speaker, I would like to invite Dr. Pruthul Desai. Sir is a secretary of IIPT RC7 and also a very active IIPT member as well as the principal of Sir P.T. Sarvajanik College of Science, Surat. So now I hand over to Dr. Pruthul Desai, sir.
Thank you, Chintan. It's a matter of proud privilege for me, Dr. Pruthul Desai, Secretary, Regional Council 7 of Indian Association of Physics Teachers, IIPT, to introduce the distinguished speaker for today, Professor Ajoy Ghatak. Professor Ghatak was Professor of Physics at IIT Delhi. Currently, he is associated with NASI, the National Academy of Sciences India at Prayagraj, the oldest science academy in India. He is passionately preoccupied in spreading the beauty of science amongst the next generation and public at large. He has authored several books for a wide spectrum of audience, from school-going children to PG students of physics. The popularity of his books bear out the fact that he is a prolific writer. His book on optics, which is a recommended book in the BSc course of our university, has been translated to Chinese and Persian. Most of the physics students of my generation learned the nuances of quantum mechanics from Professor Ghatak's book on quantum mechanics, which was co-authored by Professor Loknathan. One distinct aspect of his books, which has dazzled me in particular, apart from their contents of physics, is that Professor Ghatak has lavishly used beautiful and appropriate quotes of famous scientists to highlight the point. He is a recipient of several awards, including the 2008 SPIE Educator Award, in recognition of his unparalleled global contribution to the field of fiber optics research and his tireless dedication to optics education worldwide. He is also a recipient of CSIR 1978 Bhatnagar Award. His latest awards are Optical Society of America 2020 Sensong Lee Awards for his seminal role in the development of fiber optics and guided wave photonics, and for the pioneering optics education in India. In 2021, he received Shastra G.N. Ramachandran Award for Excellence in Physics. Finally, I may say, though he is an octogenarian, his enthusiasm and passion for physics has not waned at all, and on the contrary, seems to have surprisingly compounded. Even today, he puts in lots of efforts to prepare his talks, which usually are riveting. His mellifluous voice and the unique talk delivery adds to the magic. To add to all this, he is a gem of a person, someone who can mesmerize you with his thoughts and actions. In the end, I will quote, I find a beautiful quote by Einstein, which is relevant in today's scenario, that I found in Professor Ghatak's book titled Einstein's Year of Miracles 1905. It says, I quote, "The intuitive mind is a sacred gift and the rational mind is a faithful servant. We have created a society that honors the servant and has forgotten the gift giver." So on this note, I am absolutely delighted to have Professor Ghatak amongst us. It is, sir, it's very difficult to, introduce you with so few or such a small amount of time. But in spite of that, I have done that. I have been fascinated by your books, and at a personal level, I have been fascinated by you, all the actions that you do in particular. Thank you so much for accepting our invitation and being part of this wonderful program. Thank you.
Thank you so much, Pruthul. and for this very, very kind words. It's my great pleasure to be here today and speaking to all of you, speaking to the younger generation. And let me see whether I can put it in the final. ये क्या हुआ? Just one second. No, sorry. Just one second. Yes. Thank you very much, Dr. Joshipura, Dr. Pruthul Desai, Dr. Chintan Panchasara, for asking me to speak today. And right now it is about 3:14, actually 3 minutes, 14 minutes past 3. And so
that is great.
So
great.
I'm going to speak for 1 hour. I have planned it for 1 hour, but if you feel that I should cut short after a while, then please do not hesitate to tell me. Thank you, Pruthul, once again for asking me to give this talk on this very auspicious day of Einstein's 143rd birthday. I'm going to speak Einstein and his year of miracles. I will describe some of the contributions, not all, because the time does not permit all contributions to be described in 1 hour. In the year 1999, before the turn of the century, Time magazine asked for nominations for the Person of the Century award. And there were, as you can see, as you can imagine, there were hundreds of nominations, and they had a difficult time in selecting them. And the 3 finalists were, the first finalist was Franklin Roosevelt, who was once upon a time the President of the United States during the World War II. And in the December 31, 1999 issue of Time magazine, Bill Clinton wrote that when our children's children of the 20th century, they will see that above all, it is the story of freedom's triumph, the victory of democracy over fascism, of tolerance over prejudice. And they will see that the embodiment of that triumph was President Franklin Delano Roosevelt. If all of you would switch off your mic, that will be nice. The other finalist was our own Mahatma Gandhi as the embodiment of human rights and his faith in nonviolence. And in the same issue of the Time magazine, Johanna McGarry wrote, in an age of empire and military might, Mahatma Gandhi proved that the powerless had power, and that the force of arms would not forever prevail against force of spirit. Our passionate commitment, willingness to accept punishment for nonviolent activism were lessons that Mahatma Gandhi taught. Martin Luther King learned them, so did Nelson Mandela, Lech Walesa, Aung San Suu Kyi, the unknown Chinese who defied the tanks in 1989. Gandhi is that rare great man held in universal esteem, a figure lifted from history to moral icon. But the person who was finally selected as the Person of the Century award was Albert Einstein. And Frederick Golden, in the same issue of Time magazine, wrote, Einstein was the preeminent scientist in a century dominated by science. The touchstones of the era, the atomic bomb, the Big Bang, quantum physics, and electronics all bear his imprint. He was the embodiment of pure intellect, the genius among geniuses. So that is the person about whom I'm going to spend about an hour on. As was just now mentioned, he was born on 14th March, 1879 in the southern town of Ulm in southern part of Germany. Many people feel that he was not a very bright student, but this is Einstein's school leaving certificate when he was about 18 years old. And this certificate, as you can see probably, it shows the grade 6 here, that this certificate shows that he scored the highest grade in physics, algebra, geometry, and history. So not that he was indeed a very bright student, provided he got this subject in which he wanted to study. And then later, he had studied in ETH in Zurich, which is a very famous college in Zurich during 1896 and 1900. In 1900, he was 21 years old. And then at a much later date, he was an associate professor in this institute in Zurich. About the examinations, and that is the point that Einstein, and we also should learn from that. In ETH, Einstein later wrote that one had to cram all this stuff into one's mind for the examinations, whether one liked it or not. This coercion had a deterring effect upon me. So he did not feel like studying more on the subject because he had to remember all the formulae and things like that. This I have taken from his autobiography, of which I have a copy, the English translation, and also the German. So after the college in 1900, he tried at several places in school to teach. He was not successful. He was not a good teacher. And he was going from one place to the other. And he had a girlfriend. And in the year 1902, with the recommendation of the father of a close friend of his, Einstein finally got a job at the Swiss Patent Office. There, in total isolation, not in a big college or a research laboratory. In the year 1905, Einstein published 5 outstanding papers. These 5 papers are often referred to as the Annus Mirabilis papers. Annus Mirabilis are Latin words meaning miracle year. So 1905 is Einstein's year of miracles. And in this, as I just now mentioned, he published 5 outstanding papers. The first paper was actually his doctoral thesis, in which he described a new method for determination of molecular dimensions. That water molecule, iska size kya hai? How much? What is the size of a particular molecule? He gave a method for determining the size of molecules. In the second paper, which he himself considered revolutionary, Einstein wrote that radiation energy, that is light, consists of indivisible quanta of energy. And this quanta of energy he wrote as E is equal to h nu, where h is the Planck's constant and nu is the frequency. And in a later paper, I think in 1908, he said that the momentum of these quanta of energy, which later came to be known as photons, is equal to h nu by c. This was a revolutionary concept because at that point of time, Maxwell's electromagnetic wave theory was very well accepted. And this paper eventually led to wave particle duality and development of quantum theory. So who discovered wave particle duality? It was Einstein in 1905. And in the third paper, Einstein gave a very beautiful theory of Brownian motion, which involves movement of a big particle by continuous collisions with many smaller molecules of a gas, which move with different velocities in different random directions. So this Brownian motion, which now forms the basis of statistical thermodynamics. And in his fourth paper, he put forward the special theory of relativity, which implied that time is not absolute. And in the fifth paper, he introduced E is equal to mc square, where matter can be transformed to energy and vice versa. Some people say that each of these papers, particularly the last 4 papers, each one deserved a Nobel Prize, but he had great difficulty, as I will try to tell you later, he had great difficulty in getting the Nobel Prize. So there is a very beautiful book edited by John Stachel. The title of the book sums up everything. Einstein's Miraculous Year, 5 papers that changed the face of physics. In fact, if I want you to name another great scientist, I'm sure all of you will say Isaac Newton. So Isaac Newton's Annus Mirabilis, Year of Miracles, was the year 1666, when he was only 23 years old. In 1666, there was plague in the United Kingdom, and Cambridge University closed down the college where he was teaching, and he was sent back home to his mother's home. So when he was 23, in 18 incredible months, Newton wrote down his famous laws of motion, explained the laws of gravity, discovered calculus, and developed a theory of optics. This is the famous Principia, and also his book on optics, which came later, which was published later, but the main structure of the book was developed in the years 1666 and 1667. Many felt that the achievements of Isaac Newton could never be equaled by anyone else until Einstein in 1905 obtained results which were as revolutionary as that of Newton. However, there is a difference between the two people. Newton's successor, as Lucasian Professor of Mathematics, William Whiston, wrote of Newton in his memoirs. I have read the memoirs of William Whiston, in which he wrote that he was one of the most fearful, cautious, and suspicious temper that I ever knew. So he had no friends. Newton had almost no friends. On the other hand, Professor Bernard Cohen, after interviewing Einstein in April 1955, just before his death, wrote, "As I walked out to the street, I thought to myself that, of course, I had known that Einstein was a great scientist, but I had no idea of the warmth of his friendly personality, his kindness, and his rich sense of humor." This Professor Bernard Cohen's papers were published, probably his interview was published in American Journal of Physics. I think I had read that, and in which he wrote this. So I'm going to start with the fifth paper, which is easiest to communicate to the students. And I thought that I will say, I have myself have a simple derivation of this equation. So I will just describe that. E is equal to mc square, what it means. So you see, if you have a proton, and this is very, very elementary, I'm just saying this for students. Unfortunately, most of you are not students, so you have to pardon me for the simplicity of the talk. So if you have one proton and one neutron, and you separate them, and then you put them together to form the deuteron nucleus, then because there is an attractive force between the proton and neutron, there's a certain of an amount of energy that will be required to put them apart. And this is Einstein's E is equal to mc square. And so therefore the mass of the deuteron nucleus is slightly smaller than the mass of the proton and neutron put together. And therefore when proton and neutron combine to form a deuteron nucleus, a small amount of energy is released, which is about 2.23 million electron volt. Million electron volt, as you all know, is an unit of energy, is about 1/10 of a trillionth of 1 joule. Similarly, if you want to take them apart, then you have to supply a certain amount of energy. Like two magnets, if you want to pull them apart, then you have to supply a certain amount of energy. And in this case, it is 2.23 MeV. And energy will get, and you will create a tiny amount of mass in this process. So if I write down the mass of the proton, which is available everywhere in all books, and mass of the neutron and add them together, it comes out to be so many kilograms. On the other hand, mass of the deuteron is about the same, but slightly smaller. And this mass difference is known as the mass defect, as I'm sure. In this particular case, it is about 4 into 10 to the power of minus 30 kilograms. And so therefore, the energy that is released is loss of mass into c square, where c is the speed of light, which is 3 into 10 to the power of 8, the square of which is 9 into 10 to the power 16. If you multiply this out, you will get so many joules. And this we now do in higher secondary classes it is 2.23 MeV, because 1 MeV is 1.6 into 10 to the power minus 13 joules. Thus, this is a general theorem that you will have to supply a certain amount of energy to make a tightly bound system, to go over to a loosely bound system, and thereby you will create a small amount of mass, because those two independently will weigh little more than the proton and neutron combined together. Similarly, if there are two magnets which are stuck together, when you separate them, you have to supply a certain amount of energy, and you will create a tiny amount of mass. On the other hand, when a loosely bound system goes over to a tightly bound system, certain amount of energy will be released, and there will be a slight loss of mass. So consider the hydrogen atom. In the simplest model of the hydrogen atom, the electron, the Bohr model, the electron is rotating in circular orbits. And when the electron from the 2p state goes over to the 1s state, a photon is emitted, a light quantum is emitted, whose frequency is so much. So that the energy of the light quantum is h nu, according to Einstein's formula. And so therefore, when the electron rotating in this orbit goes over to this orbit, then a small amount of energy is released. And so therefore its mass also must become smaller. Although the hydrogen atom still consists of one proton and one electron. Before the transition and after the transition, it consists of the same matter, one proton and one electron. But since it has lost some energy, so the mass of the hydrogen atom would decrease. And if you calculate this is a very simple calculation, you will get so much. In comparison, the mass of the proton is 10 to the power of minus 27 kilogram, which is about the mass of the hydrogen atom. So there is about a 1 billionth factor which becomes smaller. This tiny loss of mass takes place. I thought I will tell you that Niels Bohr had come to Delhi University, I think it is 1960. And I was then the secretary of the Physics Society. And I had brought Niels Bohr from the hotel. He was staying in the Meridian Hotel in Delhi. And here is Niels Bohr, here is me, and here is Professor Aulak, Professor R.P. Mitra, and Professor R.C. Majumdar is probably here. So it was a historic day, and I still remember with great fondness the aura of Niels Bohr at Delhi University. So in 1905, after writing that paper on E is equal to mc square, Einstein wrote to his friend Conrad Habit that light carries mass with it. And the argument is amusing and seductive, but for all I know, the Lord might be laughing over it and leading me around the nose. That means he himself did not believe it. And it was only, although the prediction was made in 1905, it was only in 1932 or 33 that when the nuclear reaction started taking place, being observed, then people could say that that people could verify the Einstein's equation. So the experimental verification of this formula came about 30 years later. So as I said, that the deuteron binding energy is about 2 MeV, and similarly you have 2.23 MeV is the binding energy of deuteron, which I have just now said. Similarly, the binding energy of the tritium is about 8.48 MeV. That is, so much energy is required to pull apart the three particles and make them free. So the total, if I consider the nuclear reaction, the DT reaction, in which a deuteron and tritium combine together to form a neutron and an alpha particle. As you can see that I have to start with 2 protons and 3 neutrons. And in the final product, I have 2 protons and 3 neutrons. So the number of particles are still the same. The product nuclei also have 3 neutrons and 2 protons. But alpha particle is a very tightly bound nucleus. So it has a very large binding energy. And so therefore, the total binding energy of the incoming particles is 10.7 MeV, and this alpha particle binding energy is 28.3 MeV. A neutron is a free particle. So therefore, there is a net gain in binding energy of 17.6 MeV, and which appears in the form of heat. In what form does this energy appear? It appears as kinetic energy of the neutron and alpha particle. So this is a typical fusion reaction. And since both of them are positively charged, so they will repel each other. So therefore, it requires a very high energy and a very high temperature for fusion reactions to occur. That is the difference between fusion and fission reactions. Such fusion reactions require very high temperature. And inside our sun, we get this energy because not this is one of the reactions, but there are many more fusion reactions like that, which is occurring every second in our sun, because of which it releases so much amount of energy. So our sun is like a 400 trillion watt light bulb. That means our sun emits in the form of light, in the form of radiation, 400 trillion, 4 into 10 to the power of 26 joules of energy per second. This you can calculate very easily because the Earth is at a distance of about 150 million kilometers from the sun. And if you go a little above the atmosphere, you will find that about 1.35 kilojoules of energy is received on 1 square meter of the area per second. And so that is per square meter, and the total energy that goes through the sphere of radius 150 million kilometers will be something like this. So the sun emits 4 into 10 to the power of 26 joules per second in the form of light. So my question to the young students is that since it is emitting such a large amount of energy, is it losing mass? The answer is yes, of course, because of the Einstein's mass-energy relation. So the mass that is continuously getting converted to energy in the form of light is energy liberated by sun per second divided by c square. So if I multiply 4 into 10 to the power of 26 by 9 into 10 to the power of 16, so I get 4 billion kilograms per second. So सूर्य का सन का जो वजन है वो 1 सेकंड में 4 बिलियन किलोग्राम उसका वजन कम हो रहा है. So that is a phenomenal amount of mass when you compare that in the Hiroshima atomic explosion, about half a gram of matter was converted to energy. So this is a huge amount of mass, but the mass of the sun is so large that the fractional decrease in the mass is very little. And so therefore, we see the size of the sun almost the same when we wake up on the next morning. So thus every year, about 120,000 trillion kilograms of mass every year, because you have to multiply that 4 billion kilograms by 3 into 10 to the power of 7, which is the number of seconds in 1 year. So you will find that every year about 120,000 trillion kilograms of mass is continuously getting converted into energy. So you have this, it is believed that that a huge mass of gas collapsed, hydrogen atoms actually. Hydrogen atom collapsed under the influence of gravity. And as it collapsed, a loosely bound system went over to a tightly bound system, and it became hotter and hotter. And when the temperatures inside the sun were very high, fusion reactions started taking place. So it took the God created hydrogen atoms at birth, and in about 1 billion years, a gas of atoms collapsed to form roughly what the sun is today, and it has now attained a steady state, and it has been now 5 billion years since the sun has been there. But it took about 1 billion years to form the present form of the sun. Right now, our sun is in a steady state, implying that the force due to gravitational attraction is balanced by the outward pressure due to the gas. So the temperature inside is 15 million degrees, density is 160 grams. And at that temperature and pressure, fusion reactions start taking place. That is how it gets more and more heated up. That is the beauty of theoretical physics. We know much more about the center of the sun than the center of the earth. And that is the power of theoretical physics, to motivate the younger people to take up theoretical physics as a career. So the Hans Bethe received the 1967 Nobel Prize in Physics for his contributions to the theory of nuclear reactions, especially his discoveries concerning the energy production in stars. And sun is one just a small star that we have. And I show this photograph because I had the great privilege of learning. Actually, I learned quantum mechanics from D.S. Kothari, Professor D.S. Kothari and Professor Majumdar at Delhi University. And then when I went to Cornell University, I took 2 courses under him, elementary quantum mechanics and intermediate quantum mechanics. And that was a fabulous course of lectures that I heard, meticulous, a great man. And at that time, when we were students, he had not received the Nobel Prize, but he enjoyed tremendous respect at the university. And as you know, he was a German Jew and who escaped Nazi Germany and came over to United States and eventually did Nobel Prize winning work. So eventually, when the nuclear field gets depleted, it will slowly start expanding. And in about 5 billion years, it will become a red giant and envelop the Earth. So life will cease to exist in about 5 billion years. That's what the astrophysicists tell us. And then there will be a collapse and it will become a white dwarf, of which the theory of which was given by Dr. Chandrasekhar. So, you know, if you go to internet, this is a controversial slide that you find that Genesis, the Bible says this, scriptures say that God created light on the first day and God found that the light was good. So, and then they say that God did not create the sun and the moon until the 4th day. So this is not quite right. So what I wanted to convey to you is this: whatever is written, you must try to understand that they are not the truth. And I will tell you something that Bruno felt that the earth was going around the sun and not the sun going around the earth. And that was against the church. And so he was executed. He was burnt alive. Even Galileo said that it is the earth which is going around the sun, and he was imprisoned. Then his friends, Galileo's friends, said that you better take back your statement and you say that you are wrong. So, because otherwise he would have been also burnt to death. So that was the power of the church. So humko andhavishwas se dur rehna chahiye. That is what I try to tell the younger generation, that I'm saying that God exists. I definitely am a God-fearing person. But andhavishwas, superstitions, we must avoid. So, and as you all know, if a neutron gets bombard the uranium nucleus, because these reactions, fission reactions, occur very quickly because neutron is an uncharged particle. So you do not require the very high temperatures. And then the fission occurs, which was discovered by Lise Meitner and Otto Hahn. Of course, only Otto Hahn got the Nobel Prize. That was one of the Nobel mistakes. And this is a very loosely bound structure. This is a very tightly bound nucleus. So a lot of energy is released. I'm sure all of you know this. About 200 MeV of energy is released. And in the process, a few neutrons are also emitted. And so therefore, you can think of a neutrons emitted in a fission reaction can lead to a chain reaction, leading to a release of an enormous amount of energy. So in August 39, the fission reaction process was discovered in 1938. And in August 1939, Albert Einstein, with help from Lewis Hazard, wrote to President Roosevelt recommending US research on nuclear weapons. And in 1940, I thought I will tell you, I had a slide on that, but I didn't remember to put it here. Meghnad Saha created an Institute of Nuclear Physics in around 1940 or 41. He created a department of nuclear physics. He immediately realized the importance of nuclear physics, and which eventually came to be known as the Saha Institute of Nuclear Physics. So he was a great visionary, Meghnad Saha was a great astrophysicist, and many people feel that he should have got the Nobel Prize. He was nominated 6 times, once by Arthur Compton, but he was not successful. Doesn't matter. So Roosevelt immediately recommended US research on nuclear weapons, and a controlled chain reaction is a nuclear reactor, and an uncontrolled chain reaction is an atomic bomb. So first, Enrico Fermi and his colleagues designed the first nuclear reactor, which went critical on 2nd December 1942 at the University of Chicago. And Robert Oppenheimer was made the director of the Manhattan Project, which built the first atomic bomb, which was known as the Gadget. And you can see a person sitting here. So this is about, say, 10 foot tall or 15 foot tall, 15 foot diameter radius. That is the size of the first atomic bomb. And what it consists of is pure uranium. One of the bombs consisted of pure uranium-235 separated from each other. Then there is an explosion which puts the 2 hemispheres together, and enormous amount of energy is released. And so before the explosion, the Gadget was taken up the tower and set in position and exploded on July 16, 1945. And when Oppenheimer saw this explosion, he says, "I become death, the destroyer of worlds." So I'll now give you a simple derivation of the equation E is equal to mc square. As I said, that the energy of a photon is h nu, the momentum of the photon is h nu by c. So if a light source is moving towards me, then I will observe a higher frequency. So the light source, like a laser pointer, is moving towards you with a velocity u. Then the frequency that I will observe is slightly higher and given by this. And this frequency that he will observe, from whom the light source is moving away, is slightly less. This is the Doppler effect. And as you all know, we use this Doppler effect to know the shift because most of the stars are going away from us. So there is a shift, Doppler shift, from which we can measure the velocity of the stars. If the stars were moving towards me, then the lines would have been shifted in the other direction. So now let us suppose I'm inside a train. And the train is moving with a certain velocity. Let us suppose 100 kilometers per second or something like that, some speed like that. So there is an atom or a molecule which emits 2 photons of the same frequency. So the loss of energy of the atom in my frame S prime is 2h nu naught. This is the amount of energy that this atom has lost. It emits 2 photons in quick succession, and it is possible in opposite direction, each of frequency nu naught. The momenta of the 2 photons are equal and opposite. So the net change in the momentum is 0. So therefore, inside the train, the atom which was originally at rest will continue to be at rest. So with respect to you are on the platform, let us suppose. The atom will move with the same velocity u before and after the collision. So I repeat, the 2 photons have equal and opposite momentum. So the total momentum carried by the photons is 0. And so therefore, to conserve the momentum, the atom which was at rest before the emission will continue to remain at rest with respect to me. I am B here, inside the train. So a person sitting on the platform, he will see the atom moving with the same velocity before and after the emission. Now you want to measure the frequencies. So you put an observer here and an observer here. Now the source is moving towards you. So A2 will observe a higher Doppler shifted frequency, and A1 will observe a lower Doppler shifted frequency. So therefore, the change in the energy that you will observe on the platform will be h nu1 plus h nu2. And if you add them up, the LCM is 1 minus u square by c square. And if you add them up, you will get 2h nu. Now let me conserve the momentum as far as you are concerned on the platform. So this is the momentum of the atom before the emission. It is moving with the velocity u. This has a slightly higher momentum than this. So this is the momentum of this photon, this is the momentum of this photon. So there is a net momentum since nu2 is greater than nu1. This is positive. But I have just now proved that the atom moves with the same velocity. So therefore, to conserve, its mass must increase. And so therefore, delta m times u in your frame of reference, that is on the platform, multiplied by u will be h nu2 minus h nu1 divided by c. And if you subtract one from the other, divide by c, you get this. So I have just now derived this expression. Earlier, in your frame of reference, I had derived this. So this is equal to delta E. And so therefore, delta E, U. So U cancel out. And I have given you a rigorously correct derivation that if there is a change in energy, then there is a change in reduction in mass, which is given by actually the correct form of Einstein's E is equal to mc square is this form, that there is a change in energy and therefore there is a change in mass. So let me go to the second paper now. Let me see what is the time. 3:52. I started at 3:14, so I have 20 more minutes. In the second paper, published in 1905, Einstein wrote that light can be emitted or absorbed only in discrete amounts called quantum. But at that time, as you know, the wave theory was eminent. The first wave theory was given by Christian Huygens, and I'm sure all of you know what is a wave. A wave, the simplest wave is if you put a string, move up and down, you produce an X-polarized wave. And this is the displacement as a function of Z and time. This equation, if someone asks you, what is a wave? You can say that the wave is, a one-dimensional wave is described by this equation. This equation defines a wave. And if you want to be more careful, this is the solution of the wave equation. And you can see that why it represents a wave, because x of z of t is equal to so much. So I can write this at, if you take k outside, then z minus vt, where v is defined to be equal to omega by k. And then at a t equal to 0, it is a cos kz. And at this little later time, it is the same displacement, but slightly displaced by v delta t. So therefore, the displacement has moved through the distance v delta t in time delta t. So therefore, omega by k represents the velocity of the wave. So if you have two pins on a calm surface of water, then it will produce waves which will interfere. I do not have to go through that. And interference of light waves was not observed until Thomas Young performed this beautiful two-hole experiment. And he allowed monochromatic light, he allowed sunlight actually, Thomas Young, to pass through a filter. And he used two pinholes, not slits, not slits, two pinholes. And if the pinholes, as you know, it produces straight line interference pattern. He observed the dark and bright fringes. He calculated the wavelength using this formula, where beta is the fringe width, d is the distance between the two holes, and capital D is the distance between the two planes. So this is considered to be one of the most beautiful experiments in physics. And he could say that light plus light can produce darkness. And that is a manifestation of the wave nature of light. And in fact, Andrew Robinson has written a book with the title about Thomas Young, that he was the last man who knew everything. Thomas Young, the anonymous polymath, who proved Newton wrong, explained how we see, cured the sick, and deciphered the Rosetta Stone, among other feats of genius. People say that the last two physicists who knew everything about physics was Richard Feynman and Lev Landau. So light was a wave, but how could it propagate through vacuum? And then the laws of electricity and magnetism were also getting discovered. So we had Faraday's law, which Maxwell wrote in the form of an equation. Then we have Ampere's law, that a current produces a magnetic field, and Ampere put that in the form of this equation. Then Maxwell did something remarkable. He introduced the concept of displacement current. He said not only a current produces a magnetic field, but a changing electric field also produces a magnetic field. So he introduced in this equation the concept of the displacement current, and that revolutionized physics, because then one could show that an electric field of this type, which represents really an electromagnetic wave, is a solution of Maxwell's equation. See, if I assume the electric field to be X polarized, to be in the X direction, then if you substitute this in Faraday's law, you will get this. And then if you substitute both of them in Ampere's law as modified by Maxwell, then you will get omega by k is equal to so much. He substituted the values of mu0 and epsilon 0, and he found that the velocity of electromagnetic waves was about 300 million meters per second. So you see, he predicted the existence of electromagnetic waves because the solutions admitted waves, because he had introduced the concept of the displacement current. And he predicted that, and he found that the velocity of the waves would be about this. And this is the velocity of light as measured by Fuso. And so therefore, with faith in rationality of nature, he said light must be an electromagnetic wave. And the displacement associated with electromagnetic wave are either the electric field or the magnetic fields. Heinrich Hertz generated the electromagnetic waves and measured the frequency, measured the wavelength, and found out that the velocity was 3 into 10 to the power of 8. And that was the greatest experimental verification of Maxwell's electromagnetic theory. So by the turn of the century, so as you all know, that from gamma rays to X-rays to ultraviolet to infrared to microwave, and the waves that you receive on your cell phone, they are all electromagnetic waves, but differing in wavelength. And all wavelengths travel in free space with an identical velocity of 299,792,458 meters per second. And the visible portion of the spectrum only occupies a very tiny portion of the entire electromagnetic spectrum. Max Planck had said that Maxwell's theory remains for all time one of the greatest triumphs of human intellectual endeavor. People say that is the greatest unification that took place. He unified the laws of electricity and magnetism with that of light. Light is a part of electricity and magnetism. God said that let there be electricity and magnetism, there and there is light. This is what Feynman has written in his famous Feynman lectures in physics. So by 1894, Maxwell's electromagnetic theory was so established that Lord Kelvin said that there is nothing new to be discovered in physics now. All that remains is more and more precise measurement. Then Einstein put forward the concept of the photon, as I had mentioned before. This is the wave-particle duality, which led to quantum theory. I have a few more slides. What time is it? 3:14. Oh, I've finished. Pruthul, can I continue for 5, 6 more minutes or 10 minutes?
Yes, sir. Yes, sir. You can continue. No problem.
Hello. So, which led to quantum theory. He explained the, as you all know, photoelectric effect. This is the Einstein equation, and the maximum kinetic energy emitted by a photoelectric surface is h nu minus b. And this is the Einstein equation for which Einstein got the 1921 Nobel Prize in Physics. This Einstein equation was verified to a tremendous degree of accuracy by Robert Millikan, and Einstein received the 1921 Nobel Prize in Physics, and Robert Millikan received the 1923 Nobel Prize in Physics for his work on elementary charge. William Oswald who won the 1909 Nobel Prize for Chemistry, was the first to nominate Einstein for the 1910 Nobel Prize in Physics for his theory of relativity. And then after that, Einstein had put forward the general theory of relativity, which was a revolutionary contribution. And as you know, this is the general theory of relativity, the bending of light by the sun, which was experimentally observed by Eddington and during the solar 1919, but he was not given the Nobel Prize in 1919, 1920, and 1921. In 1921, there was such a bitter controversy that no one was given the Nobel Prize. And the committee changed. And in 1922, the 1921 Nobel Prize was given to Albert Einstein, and 1922 Nobel Prize was given to Niels Bohr. But he got the Nobel Prize for his explanation of the photoelectric effect and not for his theory of relativity. So there is a very beautiful book. There is a lot of politics that goes into the award of Nobel Prize, and the greatest mistake of the Nobel Committee is not giving the Nobel Prize to Mahatma Gandhi, and so on. If you are interested, and I have also written a bit about this in my book on Albert Einstein. And then Compton gave the Compton scattering, and for which he got the Nobel Prize only after Compton did those beautiful experiments in which there is a change in frequency, and he calculated the change in frequency using Einstein's E is equal to h nu and P is equal to h nu by C, and then he compared with the experimental results. Only after this experiment, people started believing in Einstein's light quantum, which came to be known as a photon in 1926. But he had got the Nobel Prize in 1921. Then, as you all know, J.J. Thomson had discovered the electron. Now we know the mass of the electron to 10 decimal places, and charge of the electron also. So on the back of your mind, you think that the electron to be a tiny particle which can be bent, etc. And then de Broglie said that since light has a both wave nature and particle nature, so electron must also have a moment, electron with a certain momentum must also be characterized by a wave nature. And he predicted P is equal to h by lambda, and he predicted by saying that the Bohr orbit has an integral multiple of wavelengths. But the experimental demonstration came much later, and that is the greatness of Louis de Broglie, that the wave nature of electron was put forward by Davison and German and J.J. and G.P. Thomson, and we showed that electrons also exhibit wave-like properties like X-rays. This is the X-ray diffraction pattern of by aluminum, and this is the diffraction of electrons by aluminum. So you see the similarity of the two patterns. And so therefore the wave particle duality was established. And so therefore the question arises, is the electron or the proton a wave or a particle? And Feynman writes, they are neither waves nor particles. And so what are those? They are described by the wave function psi, which is the solution of the Schrodinger equation. And where did that equation come from? Where did we get that equation from? The answer is nowhere. It is not possible to derive it from anything you know. It came out of the mind of Schrodinger. So Schrodinger equation cannot be derived. And as Putul mentioned, I often give Feynman quotations. And that is because if I said that Schrodinger equation cannot be derived, probably you will not believe me. But if I tell you that Feynman has written in these famous Feynman lectures, then probably you will believe me. So you see, you consider the single slit diffraction of of light. In any book on optics, you have I is equal to, this is the Fraunhofer diffraction pattern, and you try to now solve the Schrodinger equation with that. So you assume that the wave function at time t equal to 0 is 1 over square root of b, and substituting this equation in the Schrodinger equation, you can derive the momentum distribution of the particle. So what Schrodinger equation tells us is that when an electron or a proton or a photon interacts with the slit imparts a momentum. And the probability that the x is the vertical direction, the probability that the x component of the momentum lies between px and px plus dpx is the same as the Fraunhofer diffraction pattern. And then from this, you can show from the half width of full maximum of the momentum distribution function, you can show the momentum distribution, momentum imparted by the slit, and that is consistent with the uncertainty principle. So everything is contained in the Schrodinger equation, and Schrodinger equation itself cannot be derived, and that is quantum theory. So you do the double slit experiment, you have this derived in all books on optics, and then you solve the Schrodinger equation corresponding to that. You assume the wave function that the electron passes through both the slits. A single electron passes through both the slits at once. It is not that half the time it passes through here, half the time it passes through. A single electron is described by a wave function which is finite here and here. So the electron passes through both the holes or both the slits simultaneously. It interferes with itself, and you can find out the corresponding probability distribution, which is the same as the classical optics formula. This is a very beautiful result that I'm trying to say. And I have given all these steps in my latest edition of optics. And so therefore, if I did the two slit experiment with the electron, then the electron, and these are single slit experiments. This is considered to be one of the most beautiful experiments in physics. The electron passes through both the holes, a single electron. Does it become half and half? No. It is described by a wave function which is here and here. It interferes with itself. And if the electron passes through slit number 1 or number 2, like a classical particle, then P1, 2, when both slits are open, it should have been P1 plus P2. But what you observe is the interference pattern. And that can be easily explained if you assume that the electron passes through both the holes simultaneously. It interferes with itself to produce a probability distribution which is the same as the classical distribution. So if you did this experiment, which is considered as the most beautiful experiment in physics, if you did this experiment with 10 electrons, you will get 10 spots. This is not what wave theory predicts. Wave theory will predict an interference pattern, but very faint. When you did this experiment with 100 electrons, you will get 100 spots at random, but with probability distribution given by this. And eventually, when you did with 70,000 electrons, you will get interference pattern. So a single photon source, if I have one photon, another photon, and it passes incident on a beam splitter, then the photon is described by a wave packet which is here as well as here. And it can be made to interfere. So it is here as well as here. And it can be made to interfere with itself. Similarly, if a alpha particle or a proton is incident on a potential barrier, then there is a certain probability of reflection and certain probability of transmission. So the wave packet, which is initially at here, I have done this calculation myself. Then it is at a later time, it is described by a wave packet which is here as well as here. So the alpha particle is here as well as here. And when you make a measurement, it collapses from being either here or there to being either here or there. So this is the photograph of a young lady with so many photons. They are probabilistic in nature, and classical mechanics is deterministic in nature. And David Bohm writes, the most fundamental theory now available is probabilistic in form and not deterministic. So electrons do not behave just like particles. They do not behave just like waves. Feynman says it in his famous messenger lecture, which all of you should see, the students should see. Electrons in orbit are not somewhat like a cloud or fog. I'm quoting Feynman, of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one simplification. Electrons behave exactly the same way as photons. And then he says, I think I can safely say that nobody understands quantum mechanics. Okay, let me skip this, and I will conclude by a few slides on Einstein's thoughts. The above photograph was taken in California in 1933. Einstein had later written to his son that life is like riding a bicycle. To keep your balance, you must keep moving. And so you must keep working. This is my advice to all of you, students, to this thing. Work as much as possible. That will give you a lot of pleasure, a lot of satisfaction, and it will be able to keep you healthy. Einstein, 2 weeks after his second wife's death in 1936, wrote to his son, older son, but as long as I'm able to work, I must not and will not complain, because work is the only thing which gives substance to life. But there are also negative parts of his life. This is his first wife, and these are the two sons from his first marriage. By 1914, the relationship between Einstein and Mileva became very strained, and they were separated. Einstein in Berlin and Mileva with her two sons in Zurich. So it is said that Edward, the younger son, was very bright. People said that he's going to be the next Einstein. But because of the tension and the separation and everything, he suffered depression. Einstein left Germany in 1933. And by that time, he had started going to mental institutions. And then he was admitted. Einstein was in Princeton from 1933 to 1954 or 55 when he died, 55. And this fellow, Edward, was miserable in a mental institution. The war had ended in 1945. He never went back to look up his son. So his older son, who had moved to Berkeley as professor of hydraulic engineering, had once told Einstein that you are so compassionate to the cleaning woman, to the poor, but why have you been so cruel to your family? So these are all debatable issues. So many people have many essays written on his private life. So he does not, which shows that he is not the saint that people think he is. On several occasions, Einstein was asked, do you believe in God? And he said, through the reading of popular scientific books, I soon reached the conviction when he was a young student that much in the stories of the Bible could not be true. That Moses parted the Red Sea, that could not be true. Even in our scriptures, you see, Ravan taking away Sita in a helicopter. Did the helicopter exist during Ramayana? I don't think so. I don't think so. So you have to accept all these with a pinch of salt. That is what I'm trying to tell the younger generation. So to quote Einstein, my religiosity consists of a humble admiration of the infinitely superior spirit that reveals itself in the little that we can comprehend about the knowable world. Such beautiful birds, we have such beautiful eyes, such beautiful fish. They are the creators. So he looked on God as the creator. But then he said, I do not believe in a God of theology who rewards the good and punishes the evil. Read this carefully. This is Einstein. I do not believe in God of theology who rewards Ishwar bhale ka bhala karta hai. That is not correct. Because he saw in his own eyes innocent Jews getting massacred and starved to death. And of course, people started saying that where is God? why such millions of people are being put to so much of torture. So the Holocaust raised the question, was God watching all this happening? So these are all very debatable questions. I don't know much. I don't know what is the answer. Mahatma Gandhi said, I worship God as truth only. I have not yet found him. He doesn't say in the form of a person or something. He worshipped God as truth. I have not yet found him, but I am seeking after him. Even Swami Vivekananda says, one infinite, pure and holy, beyond thought, beyond qualities, I bow down to thee. But the most remarkable sentence for people like us is, I do not believe praying into any God in a temple, but it says, seek it in helping the poor, needy and sick. Chalo, it's good. So there are no Bhavishyawanis, no godmen, no astrology. Therefore, there are no miracles. No, I didn't say no God, no godmen, no astrology. To conclude, to support the war efforts of the US in 1944, he wrote again his 1905 paper on special relativity and got it auctioned. It was sold for $6 million and the entire money was given to the US government. So he had no greed. He gave away all his money. And then on his deathbed in April 1955, Einstein refused surgery and said, it is tasteless to prolong life artificially. I have done my job. It is time to go. I will do it elegantly. Shortly after Einstein's death, Margot, his stepdaughter, wrote to Mrs. Max Born. I have read this letter myself. I did not recognize him at first. He was so changed by the pain and blood deficiency, but his personality was the same as ever. He joked with me and was completely in command of himself with regard to his condition. He spoke with profound serenity, even with a touch of humor, about the doctors and awaited his end as an imminent natural phenomenon. As fearless as he had been all his life, so he faced death humbly and quietly. He left this world without sentimentality or regrets. Thank you. Sorry for exceeding my time, but I get carried away when I speak on Einstein. Thank you, Pratul.
Thank you, sir. Thank you, sir.
Sure.
Chintan, please take over.
Yes, thank you so much, sir. Starting from the very basics to the very advanced level. So now the session is open for the question and answer. First of all, I would like to request anybody from this Zoom meeting, so that to interact with Ghatak sir. Session is open for discussion.
Sir, I have one question, if you can permit me to ask. I have read somewhere that, Einstein's wife, she played a key role in his development of his ideas about his papers in 1905. But what are your views on it?
I have only read John Stachel, the book that I have written. He had made great research on what Mileva would talk. She was a good mathematician, and there are letters in these love letters of Einstein, Albert with Einstein with his future wife. He said that we will work together and we will formulate the theory. So there was some sort of a collaboration between the two, but Mileva never wrote anything of any significance. She never gave any lecture of any significance anywhere. So this rumor is propagated by Serbians because she originally came from Serbia. So my own, after reading all this, is that it is all Einstein's work, and he may have discussed some things with his first wife, but in the documentary that National Geographic has, I have seen that documentary several times, and in which they have projected that his first wife, did make a lot of contribution, and she was very upset that he did not put her name as one of the co-authors. So that is That is a contradiction of great people. You know, when he derived Lorentz transformation in his paper on theory of relativity, he did not mention the work of Lorentz. I always found that very this thing, that he didn't mention anything about Poincaré's contributions or Lorentz's contributions. And many people feel that even his theory of relativity was, he has got the total credit for that. Even Hilbert had written down the equations of general relativity. And Hilbert had written down, and he let Einstein publish it. And no one knows the contributions of Hilbert. But he never acknowledged any other person. So Einstein was a great scientist, a very simple scientist, almost a Gandhian. He had no attraction for money. But at the same time, he never gave credit to anyone else for the experiments and things like that. For example, he also did not mention the Michelson-Morley experiments.
Yes,
In his relativity paper. I have seen the relativity paper, the English translation, and he does not mention that. And Richard Cohen, he said to him, he said that had I known them, I would have definitely mentioned. So he pleads ignorance. He pleads ignorance, which I don't know. He was not aware of Lorentz transformations, which were given. He was aware of Lorentz, but he did not mention anything about that. This is true even of Newton. Newton, in the first edition of Principia, gave credit to Leibniz that he has also discovered calculus. But he did not. He took his name out. There was such a bitter controversy between Newton and Leibniz that he deleted his name and he refused to give him any credit. Then Newton had a great fight, bitter controversy with Robert Hooke. And Hooke had given him the inverse square law. And he said that you must acknowledge that I have given you this idea. And Hooke later accused Newton of plagiarism. So this is now in the internet, and this is now very well known. But Newton became famous because of his book on optics and because of his book on Principia. And but he didn't give any credit to anyone else. So I don't know. There's no doubt that Einstein was a superhuman being. He was a greatly intelligent and very sharp. But as far as his magnanimity in giving credit to either his wife or to Lorentz or to someone else, or the magnanimity of Newton to give credit, was not there. So these are very sad stories that we get to hear. From the students. During the Science Day celebration, I say that, Raman effect was discovered by K.S. Krishnan. Because K.S. Krishnan was the first person who discovered the Raman shift of spectral lines. He told his professor, and in the paper, I have a copy of that. He says that Mr. Krishnan and myself had made the observations, but he did not write his name in the first nature paper that he wrote. So many people are very sore about this. So these are endless stories. So in 100 years, people will forget K.S. Krishnan, but they will not forget Raman. But many people feel that it is Raman Krishnan effect and not just Raman effect. Chalo, yahi khatam karte hain. I'm a little tired also. but Pruthul, tumne itna kasht karke ye program kiya, but I see the participation very low. This is maybe, I don't know why. Even in YouTube, there are only, I see there are only 11 people watching and things like that. So we have to do something. We should not have too many such webinars or something like that. I don't know. Even in the morning session, I was expecting a large number of people. Chalo. We try to do our best. And,
yeah, that's what we need to do.
Yes, sir. One more. If if you permit, then we have one last question.
Chalo, one more, just one more.
Yes, sir. Someone is asking that do you agree in how the proton and electrons behave? There is something of metaphysics in it.
No.
I'm a very simple physicist. I don't know metaphysics. And so, I don't know. So complete the question. Complete the question. How the photon electrons behave, there is
Yes.
something of metaphysics in it. Oh, I don't know. I don't know. Metaphysics, what is metaphysics? You know, what is the definition of metaphysics? Metaphysics is is chasing a black cat in a dark room when the cat is not there. So I don't know. Well,
Yes. So moving ahead, now I would like to, if there are no more questions, I would like to move forward and call upon Dr. Chetan Limbachia, sir. Sir is a head of the department at the Department of Applied Physics, the MS University of Baroda, and also a national EC member at IAPT. So now I would like to call Dr. Chetan Limbachia.
Thank you, Chintan. Okay, so from the bottom of my heart, it is my pleasure to render vote of thanks for the extraordinary. I would just be miser to use any other word. It's just an extraordinary talk, sir. Thank you so much for actually giving this enlightening talk on the very great day of Albert Einstein's birthday. And I'm sure our students, those who have attended, and this will remain on YouTube. So we will again pass this talk to for the students to watch again. Okay, so this was actually so I being very thankful to you, sir. This event was actually being organized by IAPT RC7. And for that, I thank the president of RC7, Professor Vinod Kumar, sir, Dr. Prithul Desai, who is secretary, and all the EC members of the IAPT RC7. And also, it is in collaboration with the Alumni Association of our department. So I'm also very much delighted that this was actually the first activity of our Alumni Association. So I also thank Professor Joshipura sir to welcome us, and Professor Arun Pratap sir to have actually initiated this event. So, and I also thank all the participants, students who have actually participated, and we will propagate this YouTube talk to all our students. For the technical help, I'm quite thankful to Chintan and Harshal and Kavil. They have done an exemplary job. And in your talk, sir, apart from just taking us to the journey of Albert Einstein's life, you have also actually given us some knowledge on various aspects of how the theory actually evolved, how the papers, the seminal papers of Albert Einstein contributed to the knowledge of physical sciences. That included the experiments of Young and fission, and other things like a derivation of even the famous E is equal to mc square equation, and increase in mass, etc. So those were those were obviously technical things, but you have actually explained to us very lucidly, and it is, I mean, in the benefit of our students, and we are very much thankful to you, sir. So we look forward to having you in our university at some point, so that I mean, we can have a good program so that our students can actually interact with you in a face-to-face manner and personal manner. So I thank all of you participants, all the organizers of the event, and with best wishes, I just complete this. Thank you.
thank you. Thank you.
Yeah.
Professor Ghatak, your visit to Surat is long due now.
Yes.
So now that
So
the